So in this video, I'm going to solve a sample problem on the head form of the energy conservation law for a control volume that we have derived using Reynolds transport theorem. So in this problem, we have a self-priming pump that is used to draw water from a lake and shoot it through a nozzle as sketched. The diameter of the pump inlet is D1 equals 12 centimeters, and the diameter of the nozzle outlet is D2 equals 2.54 centimeters. And the average velocity at the nozzle outlet is given, V2 equals 65.8 meters per second. This is out here on the outlet. The pump efficiency is given to be 80%. And we're given the vertical distances, delta Z1, which is the height of the inlet, basically, the depth of the inlet within the reservoir, it's 1 meter, and delta Z2, which is the height of the outlet with respect to the reservoir, is given to be 2 meters. We're given the irreversible head losses in the piping system, not counting inefficiencies associated with the pump itself, are estimated as HL equals 4.5 meters of our liquid. So what we want to find is, in part A, we want to calculate the volume flow rate of the water in meters cubed per hour. So I remind you of our formula for the volume flow rate. We obtained that from studying Reynolds transport theorem for the volume. And we actually got A times V, where A is the cross-sectional area and V is V is the speed of our fluid through the outlet or inlet of interest. So here we're interested in the volume flow rate without indicating whether it's an inlet or outlet, but that's simply because we're considering a steady flow with one inlet and one outlet, which means that the volume flow rate is the same on both sides. So finding the volume flow rate on either one of these will give us the flow rate everywhere. Now we know the velocity through the outlet, so it's more convenient for us to study the outlet than the inlet because we don't know the speed here across the inlet. So V2 is 65.8 meters per second, and I also know the diameter at the outlet. It's 2.54 centimeters, so I can solve for the flow rate through the outlet, and we have the following formula. So I just saw that D2 is 2.54 centimeters. And I have V2, its value is 65.8 meters per second. So I can actually obtain the value of the volume flow rate across the outlet. If we calculate this, the final answer is going to be 100 and actually it's 0.033 meters cubed per second, but we are asked to find this in terms of in units of meters cubed per hour, so you can directly convert to meters cubed per hour. This will be 120 meters cubed per hour. In part B, we want to find the power delivered by the pump to the water. So this is, of course, the output power that is delivered to the water. In order to solve for this quantity, which is W dot of our pump, I'm going to work on the head form of the energy equation. So I remind you of the equation for conservation of energy in its head form. I have H pump used or useful plus P1 over rho G. P1 is the pressure at our inlet, plus alpha v1 squared over 2g, where v1 is the speed at our inlet, alpha is the correction factor because we're using the average speed at the inlet, z1 is the height, and on the right hand side I have p2 over rho g plus alpha v2 squared over 2g plus z2 plus the head loss plus h of a turbine. So I don't have a turbine in this question. I do have some head loss, it's given to me. I can look for Z1 and Z2. However, before I start addressing the inlet and outlet quantities, let's look at our control volume. So I'm going to select my control volume now according to the system that I have. Basically, our control volume must pass through the well-defined outlets and inlets. It must also cross through the shaft that we have here. Now I have two options here. I either take my outlet to be here, in which the water is flowing into the pipes, or the better choice that I will take is to take this whole quantity here so that my inlet is over here at the surface of the reservoir. This is more convenient because I know that if I select this to be my inlet, I know that P1 will be equal to P0, which is the atmospheric pressure, because this liquid is exposed to the atmosphere. And I can also approximate V1 to be equal to 0, because basically here water will be draining into the pipes. So the water drop will be very slow compared to whatever flow we have here. So I will have this as my inlet. On my outlet, I have V2, which is given. I can also say that P2 is equal to P0 because this water here is exposed to the atmosphere as well. Let's look at Z2 and Z1. This will be Z1, and I will have Z2 here. So basically, Z2 minus Z1 is going to be delta Z2, which I have here. So I can actually substitute this in my equation. H pump, useful. I can write this as W dot of my pump over M dot G. Remember, this is what I want to find in part B. Plus, so P1 here is the atmosphere, and P2 is also the atmosphere, so I can actually cancel these terms out. V1, we said it's approximately 0 because it's on the surface of the reservoir where water is drifting slowly down. So this leaves me with Z1, which I will take to the other side to write it in terms of delta Z2. So I will have Z2 minus Z1 on the right hand side plus alpha V2 squared over 2G plus HL. So I can write the W dot of my pump to be M dot G into Z2 minus Z1 plus alpha V2 squared over 2G plus HL. This equation basically actually tells us about the different things that the pump that we have in our control volume does. So the pump that we have is giving some kind of energy in order to adjust the height of my liquid, adjust the speed of my liquid, and account for whatever irreversible losses we have. So these are three types of energies that are accounted for by my pump. The pump is my input, which will actually give these three outputs. So the rest is basically just substitution actually. M dot G, M dot is basically the mass flow rate. I can write this as rho V dot times G into, this is delta Z2 plus alpha V2 squared over 2G plus HL. You can see that V dot is the volume flow rate which I calculated in part A. Rho is the density of water. G is gravity. I have delta Z2. Alpha is usually given to you according to the liquid we have. So here we have alpha is equal to 1.05. This should be given to you usually. So now I can just solve. I found V dot, this was 0.0033 meters cubed per second. G is 9.81. I have delta Z2, it's 2 meters. Alpha is 1.05. V2 was also given. V2 is 65.8 meters per second over 2 times 9.81 plus HL, which is due to the irreversible processes causing some head loss. This is 4.5 meters. So we can just solve for the power of our pump, the output power of our pump, and you will get 77.76 kilowatts. This is, of course, the useful power. In part C, we are asked to find the input power itself. We know that the efficiency is 80% here, so this can be written as 0.8, and it's equal to the output power over the input power of our pump. So we can directly solve for the input power. This is going to be W dot useful, which we just found in part B, over 0.8. So this is 77.76 over 0.8, and the answer will be 97.2 kilowatts.